Okay, so in this section, we're going to learn about Lagrange multipliers. And basically, the Lagrange method is a way, in some sense, it's probably a faster way, to maximize a function subject to a constraint. Okay, so remember the goal. So let's write this down. The goal is always to maximize a function subject to a constraint. So what this means is that whenever we are in a situation, in order to apply the Lagrange method, we're looking for what is our function and what is the constraint. Okay? So just to explain how the method works, we're going to look at an illustration for functions of two variables. And in this general situation, we're trying to find the extreme values. Remember, extreme could be the absolute max or the absolute min, right, with the extreme values of your function. So this is a function that you're trying to maximize or find the extreme values, subject to the constraint of the form g of xy equals k. So g equals k is your constraint for your function f. Okay, so you have a picture here. Now, looking here, if we want to find the maximum of f subject to the constraint that g of x comma y is equal to k, these are the level curves. Okay, level curves are in pink. That means we're only considering points that are along this little blue line, right? And the question is, what's the maximum value of f for points along that little blue line? The maximum value is going to occur here, right? So it looks like here, because we've got some points along this line, along this curve, and the value is actually equal to 10, right? We don't have any points on this curve, g of xy equals k, whose value is 11 or 10.1 or anything like that. So it looks like our answer for the max in terms of extreme would be 10. Now, one thing to notice, and it's not just coincidence, is that at this point where we actually have we maximize the function subject to the constraint, the tangent lines are parallel. Okay. So perhaps it's even clearer to see here. The tangent line to f is shared by the tangent line to g. Okay. G of xy equals k. So this is the tangent line of the level curves. So that means that the tangent planes, that is when they have a common tangent line. Okay. So the tangent planes of the surface f of xy and g of xy equals k, those planes have to have the same normal lines, right? So remember, the normal lines at the point, what does this mean? This means look at the tangent plane to the point, and then look at the line that is perpendicular to the tangent plane, right? So imagine some surface. Say this is some surface, and you're at some point on the plane. Now you've got your tangent plane, right? And the normal line would be a line that is going through the plane, right? And it's going to be perpendicular to the plane. So what we're saying is that at this point, the normal lines have to be parallel, which means they have the same direction. The direction of that normal line is given by the gradient. Remember, that's one of the things we learned in 14.6, is that the gradient points in the direction of, it's going to be points in the direction that's perpendicular to the tangent plane. So we've got this equation right here. So if the gradient of f at that point is parallel to the gradient of g, that means that, so this is a vector, right? This vector has to be equal to some constant times this vector. That's a way to say that these vectors have the same direction, right? Is that one is a scalar multiple of the other. So this argument applies not just to functions of 2 variables, but functions of 3 variables as well. When you're looking to maximize the value f subject to the constraint g, you're essentially going to be solving the equation gradient of f equals lambda times the gradient of g. Okay. One of the things to mention is that this approach is assuming that your gradient is not equal to 0. Because if your gradient is equal to 0, then lambda could be equal to 0, and you're not able to get any information about parallel vectors. Okay, the scalar here is called the Lagrange multiplier. Okay, and so just to give general guidelines for the method of Lagrange multipliers, step 1 is going to be find all values of x, y, z and lambda such that the gradient of f at x, y, z is equal to lambda times the gradient of g, but also, right, so this is making sure those vectors are parallel, but also g at that point needs to equal k. So this is taking into account our constraint. Okay. So this is step number 1. And then step number 2 is to evaluate f at all of the points that are resulting from step A. And then the largest of the values is the maximum value of f, and the smallest of the values is the minimum value of f. Okay, and then don't forget that we are assuming for Lagrange's method that the gradient is not equal to 0. Okay, so let's start off with just an example here, just to show the approach. A rectangular box without a lid is to be made from 12 meters squared of cardboard. Find the maximum volume of such a box. So the function we need to maximize is volume of the box. What is our constraint? The constraint is we only can use 12 meters of cardboard. So that means that the surface area of the box without the lid should be equal to 12 meters squared. Now we need to translate this into some formulas that we can actually analyze, right, where we can actually perform calculus. So for volume of a box, let's just have volume equals length times width times height. Okay, so here we go. And now for surface area, so if this is, I don't know, length times width times height. For surface area, that will be, so we'll have this, which is WH. Oh, we'll have 2 of those, right? So 2 times WH. Just put here surface area. It's going to equal 2 times W times H plus, now this is going to be L times H, right? 2L times H plus, now the bottom, remember the bottom is just going to be L times W because we're not including the top, right? Because it's without a lid. So it'll be plus W, L times W. Okay, so our constraint is going to be that 2WH plus 2LH plus LW is equal to 12. Okay. So now, going back to our method here, first thing we need to do, find all values of x, y, z such that we're satisfying this and we're satisfying this. So here, V is going to be our F and the G is going to be our surface area. Okay. So let's see here. So we need to solve that the gradient of V is equal to lambda times the gradient of G. Okay, and G is equal to 12. So let's write this with a little more details. Okay, so we're going to solve lambda V. What does V depend on? It depends on length, width, and height. Let's put here length, width, and height is equal to lambda times the surface area. The gradient of, let's call this G of length, width, and height. And we also need that G of length, width, and height is equal to 12. So this is a system that we need to solve. Okay. This means we need to compute the gradient of V and the gradient of G. Okay. So the gradient of V is equal to, so we will have three components. I need the partial of V with respect to L, the partial of V with respect to W, and the partial of V with respect to H. The partial of V with respect to L is just going to be W times H. And the partial of V with respect to W is L times H. And the partial of H of V with respect to H is going to be L times W. Now let's look at the partial of G. That is going to be, what is the partial of G? Let's see here. So the partial, so G sub L is going to be, that'll be 0 plus 2H plus W. Okay, so we'll have 2H plus W. And the partial with respect to W is going to be 2H plus L. And the partial with respect to H is going to be 2W plus 2L. Okay, so we need, let's see here, so we need WH comma LH comma LW is equal to lambda times 2H plus W, 2H plus L, 2W plus L. And then we also need that 2WH plus 2LH plus LW is equal to 12. Okay. So now, for this first vector equation, WH needs to equal lambda times 2H plus W. So we can write, do you see how in this vector equation, we've got three scalar equations? The first one is that WH equals lambda times 2H plus W. The second one is that L times H must be equal to lambda times 2H plus L. And the third one is that L times W must be equal to lambda times 2W plus L. Okay? And then remember our last one is 2WH plus 2LH plus LW equals 12. Okay. So there isn't one fixed way to always solve this system of equations. But here, one thing we can notice is that if I multiply, if I multiply this by an L, this is missing an L, so I'm going to multiply an L. If I multiply my second equation by a W and my third equation by an H, now I've eliminated a variable because L times W times H is equal to lambda L times 2H plus W, but it's also equal to lambda times W times 2H plus L, and it's equal to lambda H times 2W plus L. Okay, so that tells me that, so let's just expand this. Okay, so I have 2 lambda L H plus lambda L W is equal to 2 lambda W H plus lambda L W. So see how this equation right here is right here. And I could subtract the lambda LW. So that tells me 2 lambda LH is equal to 2 lambda WH. I can divide by 2. So that means lambda LH is equal to lambda WH. Now, I cannot divide by H because it could be that H is equal to 0. Same reason I cannot divide by L because, lambda, because lambda could be equal to 0. So what I can do is I can say lambda times LH minus lambda times WH is equal to 0. And now factor out lambda H times L minus W is equal to 0. So I can say, so lambda equals 0, H equals 0, or L minus W equals 0. Does that make sense? Now let's check, what if lambda is equal to 0? Could we have lambda equal to 0? If lambda is equal to 0, then that means this is equal to 0, equal to 0, equal to 0, which means each of these is equal to 0, which means over here we'll have 0 equals 12. So it turns out that if we're going to satisfy our constraint, lambda can't be equal to 0. What about h? Can h be equal to 0? If h is equal to 0, then this is equal to 0, right? Because that's h is equal to 0. The second equation is equal to 0. So if h is equal to 0, that means that LW is equal to 12. Okay? And let's see. So we'll for now we will keep that as an option because maybe h is equal to 0. So it could be that h is equal to 0, or it could be that L is equal to W. Now, is there a problem with h being equal to 0? Here's the deal. If h is equal to 0, then that means 0 is 2h plus W. But remember, that's also 0, so that would mean W is equal to 0. Right? And if h is equal to 0, for the same reasoning, L is equal to 0. So then we would have H, L, and W are equal to 0. Contradiction. We won't be able to satisfy the constraint. So it must be that H is not equal to 0. Just clean up my little. Okay. So it's not the case that H is equal to 0, so it must be that L is equal to W. All right, so we say, yay, that simplifies things. Now, let's look here at our second equation, because now let's look at this equation right here. So if lambda W lambda W times 2H plus L is equal to lambda H times 2W plus L. That means that 2 lambda WH plus lambda WL is equal to 2 lambda WH plus lambda HL. Okay. So we can subtract off the 2 lambda WH, and now we get that lambda WL minus lambda HL is equal to 0. And so we get now that W minus H times lambda times L equals 0. So we get that lambda equals 0, or L equals 0, or W equals H. But again, for the same reasoning as before, lambda and W and L can't be equal to 0. So it must be that W is equal to H. W is equal to H. Let's see here. Okay. So if W is equal to H, that means that we've got L is equal to W is equal to H. Let me see here. This doesn't seem, let's see here. Let me verify that I took my gradient properly. So the partial, I think I did not take my, this should be the partial of G with respect to L. Sorry, this should be the partial of G with respect to L. This should be the partial of G with respect to W, and this should be the partial of G with respect to H. Okay, so let's verify my partials here. The partial of G with respect to L is going to be 2H plus W. Okay, the partial of G with respect to W is going to be 2H plus 0 plus L. And then the partial of G with respect to H is going to be 2W plus 2L. Okay, so that's correct. Here's the problem. This right here should be a 2. So now, putting in this 2, this is now a 2. The reason why I was suspicious is because L, H, and W aren't symmetric in here. They are here, but down here, there's a difference between L, H, and W because we're not including the lid, right? So we've got 2, 2, and 1 as our coefficients. Okay, so now let me see. If I change that, now, let's see, we're going over here. There should be a 2 in front of that, so let's put a 2 here. Okay, and over here, this would be a 2. Okay, so this would be plus 2. Okay, and now we would have minus 2. Okay, and let's just erase this. Okay, so then we would have, let's pull out a lambda and an L. We'd have W minus 2H equals 0. So that would give us lambda equals 0, or L equals 0, or W equals 2H. And we said that those can't be, those are impossible. So W is equal to 2H. W equals 2H. Okay. And so now we're going to put this. So we figured out the relationship between L, W, and H. Last thing we need to do is put them into here. right, to get specific values. So if we're trying to, so we can actually go up here and use this. So if we know that L is equal to W and W is equal to 2H, so let's see here. So we said L equals W equals 2H. Okay, so then 2, let's convert everything to L. 2L, H is, so that means H is equal to L over 2. Plus 2L, H is L over 2. Plus L, W is L, is equal to 12. Okay, that's going to cancel, so we get L squared plus L squared plus L squared equals 12. So 3L squared is equal to 12, which means L squared is equal to 4, which means L equals plus or minus 2. But length can't be negative, so it must be that L is equal to 2. And W has to be equal to L, so W has to be equal to 2. And then W is supposed to be 2 times H, so H should be equal to 1. Okay? Now, we found the dimensions that are going to maximize the volume. Our maximum volume, the last thing we need to do is to insert these into our formula for volume. So we just need length times width times height. 2 times 2 times 1, so we get 4. And it should be meters cubed. How do we know it's meters cubed? Because the surface area has dimensions of meters squared, which means the length, each of these lengths is in meters. Okay? And that's that example.